Welcome to the second talk about private set intersection, is given by Benny Pinkas. Benny, please.
Hi, thank you. So in this hour, I'm going to talk about malicious security and also about amplifying the success probability. And also I'll have some conclusion at the end about PSI, which like trying to summarize many protocols from many papers. And I must say that many of the slides in this talk were written by my co-authors in different papers. Okay, so in the previous hour, we discussed about PSI based on OPRF, but the setting is like this. One party has, so here now it's going to be Alice, not Bob. She has an OPRF key that only she knows. Okay, only she knows the key. Okay, only Alice, not Bob. And then for each input of Bob, they run the OPRF, where Bob learns the output of the pseudo-random function f with this key on Bob's inputs. And then Alice sends, this is going to be Alice, these are Alice's inputs, she sends to Bob the output of the PRF on her inputs, and he compares. Now, for this to be efficient, we want the OPRF to be the most efficient. So we want to use pseudo-random function, which is the most efficient to implement. Okay? And apparently the most efficient OPRF constructions are based on OT extension, or these days on Volley. And the caveat is that they are secure as long as we implement them at most once, as long as we compute them at most once, as long as the party which doesn't have the key learns only single output. So you can think about a function like this. It might not be this specific function, and the keys is A and B. If you learn A times X plus B, it looks random. If you learn two values, then you can start computing the output on other inputs. Okay, so it's going to be very efficient, but you can only compute the function once. So obviously you cannot use the same function for all items. And the question is, which items of Bob to compare to which items of Alice. And if we're not too smart, we're going to end up with n-squared comparisons, which is not going to be efficient. So the basic idea is to use hashing. Okay, so suppose both of them use the same public hash function, they both know it, that map items to bins, say n items to n bins. So obviously, if both Alice and Bob have this blue item, they're going to hash it to a bin using the same hash function. So they're going to put it in the same bin. So therefore, what they have to do is to run an independent PSI for each bin. One PSI here, one PSI here, etc. Okay, so we end up with many small PSI problems, like n PSI problems. And if luckily Bob only has a single item in each bin, Bob or Alice, he only needs to evaluate the OPRF once, not more than once. Okay, so then we can use these very efficient OPRFs. The problem is that if we use simple hashing, n items to n bins, many bins are going to have more than one item in them. Actually, with very high probability, one bin will have log n items. So we say, okay, let's map n items to two n bins. You're going to still have this property as long as you're mapping to some order of n number of bins. Okay, so we need to do better. So the way we do better, since early papers on PSI, is to use cuckoo hashing using two hash functions. So for those of you who don't know cuckoo hashing, you should learn about cuckoo hashing. They should teach it in basic algorithms courses. And it works like this. You have two hash functions that mapping items to bins, not just one. So you map n items to something like 2 plus epsilon n bins, and each bin stores at most one item. So the thing is, each item is mapped to two potential bins, and you store it in just one of these two bins. So if x is mapped, say, h1 of x is this bin, h2 of x is this bin, you can store h in any one of these two bins, okay? When you look for x, you're going to look it in these two bins. And if y is mapped to this bin as this bin, you're going to look for y in each of these two bins. And So lookup requires two lookups, which is less good than one lookup. But the nice thing is this succeeds with very high probability. Okay, so there's a paper showing that, that result showing that if you map n items to slightly more than 2n bins, and you also have a small stash, then with very good probability, each item is going to be mapped to either edge 1 of x or edge 2 of x, or it can be found in the stash. And the stash can be very small. So a stash of size S items in the stash, ensures a failure probability of n minus s plus 1. So a stash of only size 2 ensures a failure probability of n to the minus 3, which is great. So basically, you map n items to 2 plus epsilon times n locations plus 2 more locations in the stash, and you get like cubic failure probability. So this is great. And we can ensure that Bob has just one item in each bin. Now, we cannot have both Alice and Bob use cuckoo hashing, because then Bob might put X here and Alice will put X here, and they won't be able to compare to each other. So the way we use cuckoo hashing in PSI is the following. We have these two hash functions. Alice uses simple hashing. So she puts each item of her both with location h1 of x and in location h2 of x. Bob uses cuckoo hashing. So he puts each item either in h1 or in location h2. Okay? So Alice is going to end up with very fat bins with more than one item in each bin, but Bob is going to have just one item in each bin. Okay? So then for each bin, they can do this comparison, and Bob has a single item. So they can use this single usage OPRF, this very efficient OPRF. And Bob might have a few items here in the stash, and handling the stash, it's a complete headache, so we'll just ignore it now. Okay? So this is basically how we use the efficient OPRFs for PSI. So in each bin, Bob uses cuckoo hashing. I'm just recalling the previous slide. He has one item. Alice simple hashing, so she has order of log n items. In each bin, they run an OT-based OPRF. Bob's learned this output. Alice computes F on all of her inputs in that bin. Alice sends to Bob the list of the outputs of F for all of the bins, and Bob compares them to what he learned. So is this secure against malicious adversaries? So apparently it is secure except for one simple problem. Okay? So we can do the OPRF to be secure against malicious adversaries. There's one simple problem. Suppose both Alice and Bob have a value Z. Bob uses cuckoo hashing. So he puts Z either in H1 of Z or H2 of Z. Alice should put Z in both locations. Now, suppose that Alice is corrupt and she puts Z only in H1 of Z. Now, if Bob chose to put Z in H1 of Z, then Z will be in the intersection. If Bob didn't choose to put Z in H1 of Z, put it in H2 of Z, then Z will not be the intersection. Okay? So, okay. The problem is that Bob's decision about where to put Z depends on his other inputs. Okay? So basically, the fact whether Z is intersection or not depends on Bob's other inputs, even those which are not in the intersection, and leaks information to Alice about them. Very little information, but leaks information about them. And this, solving this seems inevitable, this seems like an inevitable problem with cuckoo hashing because we put an item either here or there. And the choice depends on other items. There's no way to go around it. This is how cuckoo hashing works. So Alice, by acting like this, might learn something about Bob's inputs. Okay. So any questions up to here?
No questions so far.
Okay. So we try to solve this problem. So, okay, what about the function that we're going to implement? So a very efficient function we can use is an OPRF that can be used once by Oru, Orsini, and Peter Scholl. And it's very efficient. It's secure against malicious behaviors. This is what we need if we want to have malicious security. And each table entry, the receiver Bob learns fi of x. So for row I of the table, he learns fi of x. And the sender can compute fi on all other inputs. So this is great. And the function has another property, which we didn't require earlier, but it's going to become very useful. It has a homomorphic property. So fi is the function we're going to use for entry I in the table. So if you take fi of x and fj of y, we're going to get f with the key, which is the sum of the keys of I and j, applied to x plus y, x or y. Okay? So this homomorphic property seems to be, it's unclear how to use it. But basically, when we apply the function to two different rows, if we sum the values we get this double homomorphic property. The function is applied to the XOR of the values in the two rows, and the key is the sum of the keys in the two rows. Okay? So how are we going to use this? Okay? So all I described, I write it here. It's based on the following papers. The function is described in this paper by Osin and Peter Scholl, and the PSI applications are in these papers of me, Michael Sulek, Nitriu, Avishai Yanai, and Gayatri Garimela. Okay, so we're going to use something which is similar to cuckoo hashing, but not exactly cuckoo hashing. So Bob is using two hash functions, as is cuckoo hashing. And suppose that x is mapped to h1 of x, which is I, and h2 of x, which is j. So Bob doesn't put x either here or there, but he puts here two locations, v1 and say vi and vj, so that the XOR of these two inputs is equal to x. So it's unclear how to do that. It's not clear if this is possible. But he puts two values so that the XOR of the two values is equal to x. So instead of putting x in one of the two locations, somehow the combination of these two locations is equal to x. Okay? So for those who know, this is similar to garbled Bloom filters. You can also call this garbled cuckoo hashing. So this is what we want to achieve here. Okay, so suppose we achieve this. In the PSI protocol, Bob will run the OPRF here, and here he'll evaluate the OPRF with key I of Alice on his input here, VI, and here we'll compute FJ of VJ. And here is where the homomorphic property is useful, because if Bob sums these two values, he gets F with the keys I plus J of the X of what he put here. So what did Bob put in these two locations? He put two values whose XOR is equal to X. So basically what Bob learns is F of X with the key, which is the sum of the keys of the two table entries to which X could have been mapped. Now Alice, she knows what's the hash function. She knows that for each input of her to which two locations it could have been mapped. She knows the keys there. So she can compute this for each of her inputs. And then she sends this list, and Bob can compare this to his values. And what's nice here is that the attack that we said before, which is you should believe me, it's the only meaningful attack that we couldn't protect against before, of Alice putting a value either here or here, okay? The attack doesn't work anymore. Because what Alice sends to Bob is not f of this plus f of this. She sends to him a value which is the sum of what you get here and here. So she cannot identify whether Bob put his x here or here, because Bob is going to put x in both locations. Okay, so this needs a proof, but you can prove that Alice cannot. This provides security against malicious behavior. The only question is, how can we ensure that this is, how does Bob do this magic, this mapping into the table? So, any questions till here?
No.
Okay. Okay. So let's see. Suppose this is the table. And basically, Bob has a key, a value, and he wants to put a value in the table. Say he has We said X, and we said, okay, here we said that Bob will put X in these locations. In a general case, he has some key and he wants to put some value associated with the key. So, okay, suppose A is mapped to these two locations. He needs to put here two values whose occlusive O is equal to the value of A. That's easy. Okay, but the problem is that we have many such requirements and they might be conflicting. So how do we solve these requirements? So one option is to solve a system of linear equations. It's unclear whether they're solvable or not, but also solving a system of linear equations is very costly. So luckily here, we have a simple procedure, linear time procedure, which works like this. Suppose we have 4 items, and each of them is mapped to 2 locations in the table, and we need that the x of S1 and S5 is equal to the value of B, x of S3 and S5 is equal to the value of previously with A, here the value of B, value of C, value of D. We have all this restriction. So what we do, we recursively find slots which are constrained by just one key. So each key is an edge, and then basically it constrains these 2 values to have an exclusive O, which is equal to the value of A. Now, suppose we look at C and we say, okay, this slot, okay, this node has only one edge going into it. So there's only one constraint on it. The value of S2 XOR the value of S4 should satisfy the value of C. So basically, we don't care about this constraint anymore. We can fill the entire table with values. After we fill everything with values except for S2, we'll just, we already put something in S4. We'll put in S2 something so that the XOR of S2 and S4 will be equal to C. So since we only have one constraint, we have a node or location in the table to which we get only one edge. We can remove this because we'll fill the entire table with values. At the end, we're going to fill this, this table entry. It's going to be fine. Now, once we remove this constraint, then this entry, which previously had 2 constraints, has only 1 constraint. So now we can say, okay, about this S4, now it has 1 constraint. So we can leave it to the end, because after we fill the entire table, okay, the time remaining table, we'll have some value at S1, and then we'll put in S4 a value so that S1 XOR S1 XOR S4 is equal to D. So we can remove this. So there we can, keep removing edges from the table. We basically, whenever we have a table entry to which there's only one constraint, one edge going into it, we can remove it from the table and handle the rest of the table. So this is great. After we finish all of this, we can start filling up. So we put here in S1, S5, 2 values that satisfy the XOR is the value of A. And then we put here, this is already fixed, so we put here a value so that the XOR of these 2 is the value of B, etc. So this is like a recursive procedure. It works well, and it works in linear time, okay? And this process is called peeling, okay? It's people, in databases invented it. Basically, you peel the requirements from the table, you get to a core, and then you put the peels back. Okay, the question is whether this always works, okay? So sometimes it doesn't work. So look at this graph here. Okay, suppose this is what hashing gave us. So after we did peeling, we end up with this subgraph. And here, each table has 2 constraints. Okay, the graph, if you look at this as a graph, each node has a degree of 2 or more. There's no node with degree 1. And basically, here we cannot continue with peeling because the peeling required that there will be a table entry with only 1 constraint, a node with degree 1, and here there's no such node. So basically what we have here, if we started from the large graph, we removed edges until we ended up with something which is called the 2 core. So the 2 core of a graph is the maximum subgraph where each node has a degree at least 2. Thinking of it differently, starting from a graph, it's the subgraph which contains all cycles and all paths between cycles. Okay, and here we cannot do peeling anymore. And basically, if we start from the this big table, and we can look at the table as a graph. So these are the nodes, and these are edges. We can run the peeling until we get to this subgraph, which is the 2-core, and then we cannot do peeling anymore. Then we're stuck. And the question is whether we're going to end up with this 2-core, how big it is, and what should we do about it. So there's a theorem, okay, from graph theory, showing that for a cuckoo graph, so basically the cuckoo graph is the one where this graph, you have a set of nodes, and each edge connects to random nodes. And cuckoo means that you have like 2 plus epsilon n nodes, and we have n edges, n constraints. Each item that you want to map to the cuckoo graph is mapped to two locations. So for these types of graphs of size linear and n, with high probability, the size of the 2-core is going to be only order of log n. Okay. In other words, we can do the peeling, which is great, until we end up with a subgraph of size order of log n. And then handling all log n should be easy because it's very similar. Even if you have a protocol, we solve this with quadratic overhead, cubic overhead, it doesn't matter. It's polylog. Okay. So actually it is easy to solve it. Well, not easy, but you can solve it. You must somehow handle the 2-core while hiding which items are in it, but it's possible to do it. Okay. Okay. I'm not going to describe in detail how we're going to handle the 2-core. The question is how big it is. I have a slide which describes the entire protocol, but I won't go into details. If you're interested, you can look at the paper. The question is, what is this size of this 2-core? So looking at this, what do we actually need here? Basically, we wanted to store items in a cuckoo table, cuckoo hash table, but we wanted to hide which items we store. So basically, Bob, for each of his values, he wanted to put in this cuckoo table, I can go all the way, I won't go all the way back. Put, an OPRF invocation for that value, but he should hide which value is mapped to each location, because this will leak information to Alice. So basically, we want an Oblivious key value store. What's a key value store? Key value store, it's not something from cryptography. It's a database that lets you encode a set of keys and values, and then when you query with the key, you get the corresponding value. What's an Oblivious key value store, which we call OKVS? It's something that we define, is where you hide the key. So you have this data set, and a query for an encoded key will return the corresponding value, and a query for a key which is not encoded will return a random value. And if the encoded values for the keys are random, then whoever does the queries cannot distinguish between them. So apparently, if you look at a whole set of modern PSI protocols, they all implicitly use this Oblivious key value store. So this key value store, you have a set of keys and values, and basically what you want is a protocol where when you query for the keys, you get a value. When you get for something which you didn't encode, you get a don't care. And if these values are random, pseudo-random, this also looks pseudo-random, then whoever queries gets a value, but he doesn't know whether he received something which was encoded in the database or something which is totally random, because they all look pseudo-random. So this seems a bit odd, but I'll show you examples. Let me skip to an example first. So here's an example, then I'll go back. Okay. So here's an example. I want to encode n values. You should be able to query about this, to query my encoding. If you ask one of these values, you get the right output. Otherwise, you're going to get something random, but you don't know whether you got something I encoded or not. So here's the way for me to do it. I can encode these values as a polynomial. So I have n pairs of keys and values. I'm going to interpolate the polynomial through them, polynomial of degree n minus 1. And this is the polynomial. Okay. My encoding will be the coefficients of the polynomial. when you want to read a value, you're going to evaluate this polynomial. When you want to read a value associated with a key, you're going to evaluate this polynomial on that key. If it's one of the values I put, you're going to get the value that I put in this data structure. If you get a query another value, you're going to get whatever the polynomial puts there, gives for that value. If the values are encoded as I encoded are random, then everything that you get from the polynomial is going to be random. You're just going to see a random polynomial. And the nice property here is that when you see a polynomial, you don't know which values are used to interpolate it. So I interpolate it based on keys and values. The values are random. So this doesn't give you any information about the keys I used. Okay. So this is an Oblivious key value store. I would like to use Oblivious key value stores, but more efficient. So let me go back. So the properties I would like to get, first, I want this key value store to be linear. Okay. So the decoding function will take some linear function of this long table. Even better to get a binary one where I just get 0-1 combinations. So what I described previously with peeling, okay, it's a binary or KVS. I take two entries in the table and I XOR them. What I described about the polynomial, it's also a linear or KVS to take a random combination of the entries. Okay, and actually this linearity property is a must for all the PSI constructions. So you can look at like this is the key value store, and for each entry you get some set of coefficients. You multiply them by the key value store, and you get the value. Now, what are the efficiency measures? First, we want the key value store to be as close as possible in size to the number of items. So hopefully M is as close as possible to N. And of course, there's the encoding time and the decoding time. So for the peeling process, the encoding, except for the 2 core, is linear. That's great. And the decoding, we just look at 2 items. For the peeling, this is the peeling. It's for a system we called Paxos. The memory, the size of the table was linear. Encoding and decoding were linear. That's great. However, they had that small, big problem that we couldn't encode all items there. Okay, because once we got to the 2 core, we got stuck. The polynomial I described, in terms of size, is optimal. To encode n items, I need a polynomial of degree n-1 with n coefficients. The size is as large as the number of items I want to encode. That's great. However, encoding and decoding take me a lot of time because I need to interpolate a polynomial. Another option is, instead of polynomial, encode using a random matrix. So each item I have will be mapped using a hash function to a series of coefficients for the table I use for the encoding. And if I want to encode a certain set of items, they're going to define a set of linear equations that this table has to satisfy. And then I have to solve these linear equations to find which items to put, what to store in the table. Okay. So the size is going to be linear. That's great. But the encoding and decoding, they require me to solve systems of linear equations. And I might also have here linear equations which, I get a system which I cannot solve. But since this is random, this happens with small probability. If it's over a field, then the probability is basically f to the power of the difference between the number of rows and columns. And if it's binary, then all entries are 0 and 1. So by adding an additional lambda gates, the probability is going to be 2 to the minus lambda. So questions up to here?
No.
Okay. So, I'll continue a bit with this construction, and then there's going to be a, turn. Okay. So suppose I know in advance that the 2 core is going to be of size up to order of log n. Okay. And this I know from, graph theory or, analysis of random graphs. Then I can encode these log n items using a less efficient OKVS. So even if I use a random matrix, which will cost me quadratic time to encode, it's only quadratic in log n, okay? So in total, encoding these, say, using a quadratic, random binary matrix will require very few variables. And encoding will take cubic time, sorry, but it's cubic in log n plus lambda, so it's all going to be efficient. And the total size is going to be linear in n plus linear in log n plus lambda. Now, this is, okay, I still have to hide which items are encoded in the big table with peeling, which items are encoded in the small table. This is a bit tricky. It's all described here and in the paper. This thing I'm not going to describe, okay? You can read this. The big problem is what's hidden inside this O notation, okay? And the problem is not that we know that these constants are very hard. The problem is that we don't know what these constants are, okay? If we look at the theorem that ensured us that the size is going to be order of log n, it's all asymptotic. If you, very hardworking, start looking at the proof and try to find what are the constants in these asymptotics, you get to other statements in probability, which also has asymptotic in them, okay? And then it's like, it seems very hard to find what are the constants are. So this is, what's missing. Okay, so the problem is, this great system, I want to implement it. Okay, and I have this theorem, and I know that if the size of the two core is order of log n except with probability epsilon, then I can use a table of size order of log n plus order of log n plus lambda, and it's going to be successful. And the failure probability is epsilon by 2 to the minus lambda. That's great. Okay. What should be, what are the constants here? Okay. So in this PRTY table, we use some heuristics. And based on the heuristics, we found out that if the table size is 2.4n, then the failure probability seems to be 2 to the minus 40. But the elephant in the room, essentially for almost all previous PSI results that use cuckoo hashing, is a rigorous analysis to translate the asymptotic theorem to concrete parameters, okay? And this is like a huge problem, okay? So what we want to achieve is something like this. There's a very nice result from last year showing that 3 cuckoo hashing, if you map items with 3 hash functions to a table of size 1.23n, you succeed with very high probability asymptotically, okay? Now we want to find, we want to implement this, okay? So suppose we want the failure probability to be this. We want to use this construction. I want to map 1 million keys. They say, 1.23, I want to use 1.3 million, just to be on the safe side. Will this ensure me that this succeeds with at most 10 keys in the 2 core? I look in the theorem, you cannot find it from the theorem or from the proof. It's, it seems extremely hard to identify the constants there. So one might say, okay, let's run a simulation to find what's, whether you get this small failure probability. The problem is that if you want to run a simulation to verify a 2 to the minus 40 failure probability, you have to run at least 2 to the power of 40 experiments, okay? And this is 1,000 billion experiments, each one of them running a million items. It's a huge cost. Once we did it with Christian Weinert and Thomas Schneider, and there they had a cluster where they run more than 2 million core hours to do the simulation. But you cannot do it for each system that you build, okay? And what if we need 2 to the minus 80 failure probability? Again, that would be impossible even with the strongest cluster to verify experimentally. And this happens for many construction of PSI. We use hashing. It's a probabilistic process, sometimes it fails. When we use hashing, say, for caching in operating system, then if you have a failure, the system runs a bit slower. If this happens 1 in 1,000 cases, it's not a big deal. In PSI, each hashing failure results in either inaccurate output or information leakage, which is something that we don't want to have. Now, there are places where maybe we don't care about inaccurate outputs. The system application I told you about, we don't care about false negatives because we can just compare to, say, 90% of the CSAM database, that's fine. In machine learning, they don't care about approximations. But in general, when we're talking about PSI, we want an exact output because otherwise there's a privacy leakage. So we have a problem because all of these, great hashing techniques, cuckoo hashing, etc., the people who designed them, all the results are asymptotic without any concrete bounds on failure probability and on sizes. And we need these concrete bounds if we want to. So for theoretical analysis, we want to have a negligible failure probability, smaller than any polynomial. For concrete analysis, we want the probability to be, say, below 2 to the minus 40. So when you run experiments with cuckoo hashing, it's very good that we see very sharp threshold. If we have this, bound of 1.23, if you run an experiment, you see that the threshold goes like, this when you run it. That's great, okay? But when you want to specify, how big should the table to be to have a 2 to the minus 40 failure probability, you have to run a lot of experiments, which are very costly. So you can either work heuristically, you can either run experiments, and that's a new system that we going to describe here. We can work with amplification. So one thing to note before using amplification, okay? The good side is that cuckoo hashing, the construction, they have very sharp threshold. Table is a bit above the threshold, and it seems to always succeed. So for practical applications, this should be fine. But if you want to verify the failure probability, there's no theorem that can help you do that. One thing that you should note, and that's a cautionary tale, okay? The failure probability is a function of the input size. It's something like, n to the minus 3. This means that for larger inputs, you're going to have very low failure probability. For smaller inputs, cuckoo hashing is going to fail more often, okay? So if you're using smaller inputs, you should be more careful. Or you should use less efficient PSI because you don't care, because the inputs are small. But these hashing techniques, they don't work for small input sizes. Okay, so the new approach is amplification. We cannot run an experiment to verify a failure probability of 2 to the minus 40, but we can efficiently verify statements about large failure probability, okay? So if, say, I want to say that a certain scheme maps, say 1,000 keys into 1,300 bins with a very small 2 core, and I claim that the failure probability is smaller than 2 to the minus 15, then this I can verify by running, say, 1 million experiments on my laptop. So verifying a large failure probability is rather easy. What is hard for me is to experimentally verify a small failure probability. So the main idea will take smaller OKVS instances for which we have large failure probabilities, which we can empirically verify using experiments, and we will compose them into an OKVS for many items, and we will prove that the large one has a small failure probability, like 2 to the minus 4. So we take components that you can verify using very efficient experiments and build a large component for which we can prove a small failure probability based on the experiments. Questions?
No questions.
No. Okay. Actually, I can see you, so you can raise your hand and then I'll answer. Okay. So here's the construction. So we could call it a star, but it doesn't look like a star. They should be around this guy. Okay, say we're going to have 4 OKVS instances, 4 hash tables, each large enough to store 1/3 of the items. So basically, the total size is like 4/3 times n. So it's going to be larger than n. And each one of them is large enough to store n over 3 items with the failure probability p. So p is going to be like 2 to the minus 15 or something like this. These are fewer items, so we can verify this using experiments. And we want the whole construction to have a failure probability of, say, p squared, which is going to be 2 to the minus 30. And so we're going to have a hash function which maps an item to one of these T1, T2, T3, these 3 tables on the bottom, not to the one on top. Okay, and each one can store 1/3 of the items. So how are we going to decode? So we have a key and we want to read the value from the table. What we're going to do, the hash table, the hash age is going to map the key to one of the 3 tables down here. So we're going to decode from this table. Say the item is mapped to this table. We're going to decode from this table whatever it tells us about the key K. We're going to decode from T0 whatever T0 tells us about the key K. And we're going to XOR the 2, and this is the result. So basically, when we want to decode K, we go to the table on the bottom to which K is mapped, decode what it tells us about K, go to the top table, decode what it tells us about K, and we XOR the 2 results. So this is how we decode. The question is how we put items there that things work. So here's the encoding. Now note that I'm talking about mapping a set of n over 3 keys to a table. We put keys and values associated with them in the table, but the success of the encoding only depends on the keys. The keys define to which entries in the table each item goes. After, if we can map the keys into the table, we can put there any values that we want to be retrieved by these keys. But the success only depends on the keys before we know the values. Okay, so the first thing that is good is if encoding succeeds for all of these 3. So it only phases probability p, so probability 1 minus p to the power 3, it succeeds for all of these 3 tables in the bottom. Okay, and then what are we going to do? So first, in the top table, we're going to put random values. We don't care about it. And then for the bottom tables, say for this table, each item which is mapped to T1, we know that in the coding, we're going to read something from it from T1, we read something from T0, and we're going to XOR. We already put in T0 random values. We're going to know what K is going to retrieve from T0. So we're going to put for K in T1 exactly the thing that, when we XOR with what we retrieve from T0 will give us the right value for K. And the same for T2 and T3. So basically, first we encoded in the top, and only then we encode in the bottom. Okay, and we can put any values that we want. Now, suppose that it happens that the encoding succeeds for the keys mapped to T1 and T2, but for T3 it doesn't succeed. Okay, for T3, the set of keys that are mapped to it, we cannot, they don't map, we end up with a large cuckoo, whatever, it doesn't happen. So the way we work is like this. First, we put random values here. Now we know that the values that are going to be mapped to T3, the way we're going to decode them, we're going to read something from T3, retrieve the information associated with them in T0, and XOR the 2. Now for T0, the encoding succeeds. Okay, so we're going to put in T0 values so that for the items mapped to T3, the XOR of what we put for them in T3, which is completely random, and what we put for them in T0, the XOR is going to be what we should encode for them. And now, after we put values in T0, we still need to take care of the items mapped to T1 and T2. So we're going to put in T1 values so that the XOR for the items map to T1, the X of what we put here, and what's already here will give us the right decoding. And the same in T2. Okay, so basically we start from the table in the bottom that we failed to map to. We put the random values. Here we put values which fixed encoding to the items that are mapped both here and here. And here we put values with fixed encoding for the items mapped here and here. And of course, we can do the same if the encoding fails for T1, but not for T2, T3, and T0, or it fails only for T2. So basically what we got here, the previous slide, was a system that works if the encoding fails for at most one table. If the encoding fails for two tables, say for these two, then the procedure I described doesn't work. But the probability that the encoding fails for two tables, okay, is, choose 2 times P3 plus the probability of failure for 3 tables, etc., but it's much smaller, okay? So basically, we ran experiments verifying a failure probability of P, and we get that the failure probability for the whole system is 6 times P squared, so it's much smaller, okay? And the size is 4/3 times the size of an optimal OKVS for an item. So it's 4 times an optimal OKVS for 1/3 of the items. And in order to know, what parameters to put here, we need to verify a rather large failure probability, P. And we get a smaller failure probability of P squared. And here I used 3 tables in the bottom to make things simpler, but you can generalize it to any number of bins. So this is one example we used. So we start from 1 million items. We have at the bottom 160 bins. So on average, each bin is going to have 6,250 items mapped to it, but we make each bin this large. Why did we make it this large? Because we ran experiments on these small bins, verifying a failure probability of something like 2 to the minus 5, 15 to the minus 20, which is very easy to verify. And based on a theorem, just analyzing what's the probability of 2 of them failing, we get that the failure probability for the entire system is 2 to the minus 45. Okay? And the encoding is very efficient, and the total size is 1.388 times n. Okay? So overall, we get something which is it's linear, and it's very close to n. And the total, and we can experimentally verify a very small failure probability, even though we only we can just work with a laptop and verify this. So this is the amplification of the failure probability. Now, we can design recursive construction and somehow try to push this further. For practical systems, it seems that this single level I described is sufficient. The open question, which I don't know how to solve, but maybe it's solvable, it would be very nice to start from a polynomial size OKVS, which has a polynomial small failure probability. So if you recall, cuckoo hashing has a failure probability of n to n minus s, where s is the size of the stash. So we start from polynomial failure probability. And somehow I would like to take polynomially many such small OKVSs, combine them, and get something with negligible failure probability. Because all the tricks I describe here, we start from polynomial failure probability, we end up with polynomial failure probability. Much smaller, and this is all that we need for practical applications. Getting to negligible failure probability, that would be very nice. I thought about it quite a bit. I don't know how to do it, but it might be possible. And okay, this OKVS, okay, huge sets of, almost all recent PSI papers use this construction. Okay, and by this amplification, we basically move from heuristics to rigorous construction. The heuristics works. I'm pretty sure it's fine. But here we can prove things using experiments. The main takeaway, okay, ignore everything. The main takeaway is that we get malicious PSI with runtime, which is similar or even better than the previous PSIs with only semi-honest security. So PSI is a great example where malicious security gets you almost the same. We get it with almost the same overhead. Okay, as semi-honest. Okay, so questions up to here? Okay, so what I want to do in the last 10 minutes is a quick recap of the big PSI picture. Okay, so suppose we need to implement PSI, what should we be using? Okay, simplicity. Okay, this is something which is not described in papers. In papers, actually, many times you want techniques which are very cool and interesting, etc. Okay, and we want to optimize performance. If you really want to build it, you want a simple solution. Well, first of all, okay, for you to understand, for you to implement, and this Diffie-Hellman-based solution is extremely simple, and also to explain this to your managers or customers. Okay, you don't want to go tell them amplification, cuckoo hashing, whatever, expander graphs. This is something they can understand. And this is extremely important, okay? And these Diffie-Hellman constructions are much simpler than others. So that's a great property of them. Also, we're using probabilistic constructions. As I said, if we want concrete failure probabilities, sometimes heuristic is fine. Sometimes we can have hashing failures, say for malicious, for machine learning or for CSAM detection. If you want to have a rigorous analysis, it's quite complicated. What we should remember, I'm talking here about someone who wants to implement this, the failure probability decreases with the input size. If you work in with small input sizes, make sure that the failure probability of your system is still small, because it might be much larger, because 1/n is not that small where n is small. Okay. What input size should I plan for? So, okay. The cool PSI systems with the best performance work well for larger inputs, because we use OT extension or Volley, which have a pre-processing phase, which doesn't, if you have a small input, it doesn't make sense to use it. Okay. Also, the hashing failure is smaller for larger input set. If you have smaller input set, then the hashing failure is large. So the bottom line is that if you have smaller input sets, again, this Diffie-Hellman simple solution might be better than the more efficient protocols. For smaller input set, there's a recent Diffie-Hellman-based protocol of Mike Kusulek and E3U, which were co-authors on the best papers for OT-based PSI. And okay, and this is the OT-based PSI performance. This is the Diffie-Hellman protocol that they designed, a bit different than the one I described. And this is the input size. And they implemented both, and these are their protocols, both this and this. And the Diffie-Hellman one is better for smaller input sizes. Okay? Because all this strong machinery, Volley, OT extension, etc., doesn't kick in until your input size is, say, 1,000 items or more. How to measure performance? What's more important? Communication or computation? Okay, what's more important? So Google, in their paper, they say, whatever, communication costs are far more important, because they can, in the data center, they can put as many cores that they require. The communication is the bottleneck. On the other hand, Apple, okay, remember each PSI message goes with a photo. The photo is 1,000 times larger than the PSI message. They don't care about communication. They do care about computation, because this translates to battery usage on the phone. So for that application, computation is more important. And in general, this is a paper we had. We said, okay, we both are important. Which one is more important? Let's try to compare them together. So let's compare dollars. So cloud service, AWS, they charge you something for CPU. They charge you for communication. These curves are curves which are equi-cost. You have the same cost spending this time of communication, this amount of computation, amount of communication and amount of computation here. So all points on this curve have the same cost. When you design a protocol, you want that the sum of the cost for communication or computation will be the smallest. So you want to be as close as possible to here. So here you can compare both of them together. Okay, do you want semi-honest security or malicious security? It depends on the application. But luckily for PSI, the performance gap is very small. Okay, so for Oblivious transfer-based protocols, like the one I described to you with that saying that the Oblivious transfer-based protocol, it's almost the same overhead. For the Diffie-Hellman-based protocols, then the recent one by Rosulik and Trio, the malicious one is only 20% lower than the semi-honest one. So to sum up, what should you use? After this slide, okay. So the Diffie-Hellman-based protocols, so the blue is good. They have the best performance for small inputs. They are very easy to implement and explain. You can modify to compute the intersection size very easily, but not to do many other things. The Oblivious transfer-based protocols, they're much, much more efficient for larger inputs by orders of magnitude, but they're more complicated and they're harder to modify. And you can also look at combining PSI with generic MPC, and there you can compute any function that you want. That's the main advantage, not just the intersection, but any analysis of the values. But they are slower and they're more complicated. And yeah, so question? Yeah.
Okay, so we have a question about the previous lecture. So you mentioned in slide number 4 some applications to PSI. And the question is about the probabilistic analysis. And the question is, which protocols or real-life situation would fit that example?
With the probabilistic analysis. Okay. So actually, the Diffie-Hellman-based protocols, usually they're very... Okay. Why we needed the probabilistic analysis? Because we use cuckoo hashing and variants of it. Why did we use cuckoo hashing? Because it's better than hashing. Why did we use hashing? Because with Oblivious transfer, we have very efficient OPRF protocol, very efficient pseudo-random functions that we can only evaluate once. When we use the Diffie-Hellman-based protocols, it's a function that you can evaluate many times. So you don't need hashing. So you don't have the problems that come up with this probabilistic analysis. When you use these OT-based protocols, which are efficient maybe by 3 orders of magnitude, definitely by 2, okay? You use pseudo-random functions that can only be evaluated once, and therefore you need hashing, and then you run into this probabilistic analysis problems. Yeah. Okay. So here we are, and something I did not describe is a completely different model for PSI, outsourced PSI. Suppose there are many parties, and they don't want to compute PSI themselves. Each one of them shares his or her input between, say, 3 servers. And then the servers will compute PSI between them. The intersection of kinds of analysis. So this is the completely different model. It's a different trust assumption. I don't trust myself. I trust that these servers do not collude, but the resulting protocols can be very efficient.
Okay, Benny, thank you very much for 2 great talks on PSI. We're going to take a break now and resume with Peter's talk about the pseudo-random correlation journey.